Hi everyone, I'm happy to be here to share with you this presentation. I am Fatih Rashid, PhD student, and Mr. Darif and Safi are my advisor. So welcome in my presentation titled Channel Identification of Nonlinear System with Binary Value Output Observation based on Positive Definite Kernel. So to abort this presentation we have this plan. Firstly we start with introduction. Secondly we present problem statement. Thirdly identification algorithm. Then we compare the algorithm by numerical simulation. And finally we conclude our study. Introduction. Nowadays system identification play an important role in control system with application in many fields. For example in biologics, physics and computer engineering. In this study, a nonlinear system is exploited while using the reproduction kernel and linear adaptive method to identify the practical frequency selective fading channel called broadband radio access network. Problem statement. The identification of system using binary output has been an important research topic for several years. The main motivation is found in many applications and systems due mostly to the recent explosive development in computer and communication network. So let's consider a nonlinear system with binary value output represented in this figure. It consists of finite impulse response followed by a nonlinear static function. The following equations are used to model the system, where E, B, and F represent the input signal, the measurement noise, and non-linearity respectively. And the output S is described by the following equation, where C is the finite tertiary. During this paper, we will assume the following system proposition. The additive noise is Gaussian and independent of the output and the input. The nonlinearity is continuous and irreversible for infinite x. There is no delay in the system and tertiary is noise. All these assumptions are employed to simplify system analysis and to find the best result. Polycon et al. Algorithm. A recursive identification algorithm was presented by Polycon et al. Algorithm in 2016. The basic idea is to of this algorithm is to formulate the identification problem as a bounded error identification problem. The update equation for the Polycon et al. Algorithm are as follows. The filter weight vector is updated using the first equation. The vector of the main gun is estimated using the second equation. The covariance matrix is computed according to the third equation, and the epsilon represents the error, where sigma is described by this equation. The main disadvantage of this algorithm is its performance degradation when resolving nonlinear problems. So kernel methods are increasingly developed. They are a significant source of advance, not only in terms of computational cost but also in terms of the obtained efficiencies in solving complex tasks. So the basic idea of kernel method: at each instant, the learning procedure is performed in two consecutive phases. First of all, we get the desired output is from the nonlinear system with binary value output and the noise. In the second phase, and after the transformation of the data to a nonlinear Hilbert space with a Mercer kernel, the model coefficients are update while minimizing functional cost by using the proposed algorithm. Reproduction kernel Hilbert space. Consider a linear cross H of a real value function if defined on set X. In particular, H is a Hilbert space for which there exists a function kappa with the following two property. For every X in observation space. The kappa belongs to the Hilbert space. K has so-called reproduction property if the following property is achieved. The proposed algorithm. The basic idea of the proposed algorithm is to run the polygon al algorithm in the kernel feature space, which is connected with a positive definite kernel kappa. The proposed algorithm is composed for the four following steps. In the first step, we transform the input space from the observation space to a Hilbert space to generate the input data from the nonlinear system with binary value output observation. In the second step, we apply the logic of the polygon algorithm to the sequence defined in equation number 3 to minimize the cost function, where the alpha represents the weight vector in the reproduction kernel Hilbert space. In this third step, we operate immediately in the reproduction kernel Hilbert space, assuming the data has been mapped in the kernel reproduction Hilbert space using the function map. Using the derivation in the reproduction kernel Hilbert space, the update rule for the proposed algorithm becomes: the filter weight vector is updated using the equation number 5. The vector of the mangan is estimated using the equation number 6, and the covariance matrix is computed using this equation, and the error is described by the equation number 8, where sigma represented by the following equation. Numerical comparison and numerical simulation. Numerical simulation are presented in this section to illustrate the performance of the proposed algorithm. We simulated the system in which the linear dynamic part is a branch channel, and the output is a hyperbolic function, and the input sequence was randomly generated with uniform distribution. The following equation describes the impulse response of the branch channel, where m delta and tau represent the magnitude and Dirac function and time delay respectively, and we applied two algorithms in the following situation for various scenarios and for different data input. Impulse response parameter estimation. The estimate parameter of the branch channel impulse response using the proposed algorithm and polynomial algorithm is presented in the first figure. For a data length equal to 1000 and an SNR equal to 10 decibel. From this figure, we remark that when estimating the branch channel using the proposed algorithm, there is a slight difference between the estimated value and the measured value, and an apparent difference when using the polygon algorithm. Figure 2 show the estimation of the branch channel impulse response as a function of number target for a data length equal 1000 and for an SNR equal to 10 decibel. The impulse response is estimated with good precision using the proposed algorithm, but represents some fluctuation if we use the polygon algorithm. And in figure number 3, we present the estimation of the branch radiation impulse response using both algorithm for a data length equal to 1000 and for an SNR equal to 30 decibel. From this result, we note that the estimated amplitude has some form as those of the measured data, the impulse response parameter are estimated with a high performance using the proposed algorithm. For the polynomial algorithm, we have a difference in some path delay. For example, in the first four path. Magnitude and phase estimation. In order to test the robustness of the proposed algorithm in the frequency domain, we show the estimated magnitude and phase of the branch channel impulse response in the case of the n equal to 1000, 2000 and 3000. From figure number 4 indicates where the number of data is 1000, we can conclude that the estimated phase of the branch channel impulse response via the proposed algorithm is closer to the tree honest. However, using the polynomial algorithm, there is a significantly large difference between the measured data and the estimated phase. When number of data is equal to 2000, we can observe that the estimated magnitude and phase of the branch channel have the same appearance and are very close to the tree value when using the proposed algorithm. Whereas when using the polynomial algorithm, there is a minor difference between the estimated and the measured honest. Moreover, we note that the estimated value of the branch channel using the proposed algorithm and polynomial algorithm are in excellent agreement with the real model and close to the tree honest respectively when the data length is large. In this example, the data input equal to 3000. In conclusion, the input data length n and the signal to noise ratio SNR have a great impact on the estimated phase and a small impact on the estimated magnitude. Conclusion. In this study, we have proposed a new kernel algorithm based on positive definite kernel for the branch channel identification using the nonlinear system with binary value output. The simulation results show that the proposed algorithm is effective and efficient for identifying the branch channel. So, the future research include the development of an extension of this algorithm to memo system, multiple input, multiple output, and development of new methods for identifying communication channel using kernel method can be presented in the future. And thank you for your attention.